everyone. I'd like to begin with Chapter 10, what we call dynamic program. Dynamic programming is a useful mathematical technology for making a sequential decision. It provides a systematic procedure for determining the optimal combination of decisions. In contrast to linear programming, there does not exist a standard mathematical formulation of the dynamic programming problem. Rather, dynamic programming is a general type of approach to problem solving. To make these descriptions more concrete, I now illustrate a prototype example, shortest route for a network problem. This is a network. John lives in the New York, denoted by circled A here, and plans to drive to Los Angeles, circled E here. What is the shortest route that he can travel? That's the problem. Okay, first we use the short-sighted approach, which is selecting the shortest distance offered by each successive stage. Follow this strategy would give example. If we is here, he starts from here, then he will choose the shortest route, 152, then it's here. Then arrive to the city B3, then he see 11, 12, 13, so choose this path to the city C3, then 8, 10, so choose this path to here and to here. So follow the short-sighted approach. We can get the route A to B3 to C3 to D1 to E at the total length of 25. This is the shortest route with the short-sighted approach. However, we can see that if we choose this path to B2, then to C3, guessing a little on the first stage may permit greater saving than after. 5 plus 4 is 9. Here, 1 plus 11 is 12. So, the total of A to B2 to 3 to C3, the length is 9. It's shorter than this path. We can calculate the total length for each route. Of course, we can use this method by calculating the total length for each route to obtain the shortest one. However, the possible routes in this problem is 18. Is a very large number of routes. So, emulation has no generality. Now let's use DP method to determine the shortest routes from node A to node E. Before we start this method, we need to give some notations, such as N denote number of stages, N label for current stages 1, 2, 3 to n. Sn, current state for the stage n, xi, the decision variable, xn star, the optimal value. And this function, fn, sn, xn, means immediate decision xa plus optimal future decision of the next stage. It equals this one. And fn star is the optimal value of fn. Fn star usually in this problem it equals to the minimum of fn. Okay. Now let's find the shortest route between A and E by going backward. Firstly, we find the optimal policy for the last stage E is 0. We use this notation. F star 5 is 0. Then backward, we determine the shortest route to E from each of the states in the stage 4. There are 2 states in the stage 4. First, D1. So we use this formula. We know that FD1 equals the distance plus FNE, F5E. So it equals 5. We denote it F4 star D1. Similarly, use this formulation, we can get that the path from D2 to E, the length is 2. Then back to the 3 stage, we determine the shortest route from each stage CT. The C1. Here, F3 is the stage 3. At stage 3, now we need to find from the stage 3 to the destination E the shortest route. First, from the state C1, we can know that F3 C1 equals C1 can go to D1 to D2. So it equals C1 D2 and C1 D1 plus the optimal distance. And we plus it, then get the minimal, so it equals 8. So the optimal decision for C1 is go to the D1. It's the optimal decision. Similarly, for the C2, we can get its shortest, the optimal decision, that is C2 to D2, and the distance is 7. Follow that, we can get C3. The optimal decision is C3 to D2. Then stage 2. There are also 3 states. For each state, B2, we use this formula. The length equals B2, C1, C2, C3, and sum, and as the shortest route from stage 3 to the end. So we get the optimal decision is B1 to C1. Okay, similarly, we can get the optimization of B2 and B3. That's helpful. Okay, now go to the first stage, A. Use the same method. We can get that the optimization is the minimal is least 1, so it's least 1 and least 1, and we get the optimal decision is A to B2. Okay, so we can get from the total graph that the optimal route is A to B2 to B2, then to C1, to D1, then to E. That's the shortest route for this network. The total route length of which is 19. Of course, it's shorter than that we get with the short-lighted method. Now, summarize this method. We can see that the shortest route problem can be divided into 4 stages. Each stage has a number of states associated with the beginning of that stage. The policy decision at each stage was which route to choose. We use the recursive equation. The solution procedure states at the end and moves backward stage by stage, each time finding the optimal policy for the stage until it finds the optimal policy starting at the initial stage. This is the recursive equation. We can see that the stage n, the shortest length of stage n, equals n to n plus 1, then plus the optimal or the shortest length from n to 1 to the end. So this is the recursive equation. We find the shortest route based on this formulation. Okay, that's all for today. Thank you.